All right. Okay. Welcome everybody. Welcome to CS596 Machine Learning. And my name's Yang Xu, and I'm the instructor for this course. I'm currently an assistant professor of computer science in SDSU. Here's on the slide, you can see my email, and the second URL is the website for our lab. And if you are interested in machine learning and doing graduate projects, you're welcome to contact me by email. Okay. All right. Everybody can hear me correctly, right? So if you have questions, can speak, or you can type into the chat so that I can see it. Okay. So this is the first lecture, and it's basically I want to do an overall introduction to first the course contents, how it is structured, how it is graded, grading policy, and how many assignments and the weight of assignments and final exams. We'll talk about that. And then we will start from introducing the concept of machine learning by watching a couple of very cool applications, especially the most recent breakthroughs in the field. And it's a really exciting field. That's new papers, new techniques, new fancy applications are coming out every day. Okay, so why not let's just talk about the course first. Okay, so here's a bit information about myself. Okay, so I would say, to put it simple, the whole course, if we want to see the landscape of it, to see the outline of it, I would say we can categorize all the content covered in this course into two parts. The first one is supervised learning, and the second part is unsupervised learning. So the terms supervised versus unsupervised are the terms that are commonly, like very frequently used in the field of machine learning. So basically the term supervised means that in order to train such a model, we need to have data and have the data labeled. And to labeling the data is the job of human beings. We need to basically collect data and also hire people to do the label. Say we have tons of pictures of animals, and before we want to train a machine learning model that knows that a picture of a dog is actually a dog, then we need to have a data set that human beings have labeled. Okay, so those labels are the ground truths. Those labeled data are the ground truths, are what we are training against with. Okay, so as long as the training process involves the human labor, involves the supervision from the human knowledge, then we say it's supervised learning. And the other category, unsupervised, apparently it means that we don't have human labeled data available, and we purely want to recognize the patterns within the data itself, within the data themselves. And in such a case, then we don't need to deal with the label, and it's a kind of an unsupervised learning task. And so sometimes the boundary is not that clear, but overall speaking, if we look at the sub-problems in this page, we can clearly do the separation. So in the supervised learning parts, so it's basically organized by how the contents in this course are organized. So we will look at the linear regression model first, and then we'll come to a binary classification task using logistic regression, and multinomial classification task using softmax regression. And then SVM will be the classical model that people used before very frequently for supervised learning. Okay, so as long as you see the name like those models, you will immediately see that it's actually falls into the category of supervised learning. And neural network will be a big focus of this task. So we will see how basic neural networks units are composed of, how they are constructed, and then how do we use the basic models to build deep and complex models, and how the convolutional neural network models are built and applied to computer vision tasks, and how recurrent neural network models are built to apply to the natural language or sequential modeling related tasks. Okay, so by looking at the names of those subcategories, we can basically have the idea that they belong to they are most often used in the category of supervised learning task. Okay, and this unsupervised learning task, what we're gonna cover in this course basically include the principal component analysis. It's okay if you don't recognize or you don't know about the term, the name yet. So it's okay, we're gonna cover it. So t-SNE is something that related to that do a similar job to PCA, but it is totally use a different underlying algorithm. Okay, and more importantly, clustering is another focus of the unsupervised learning, which basically identifies how data groups into clusters, how they groups into patterns. Okay, and in a word, for those smaller tasks, we don't have human knowledge involved to label the task. Okay, so that's a little bit about the overall like a one-page summary of the course contents that will appear in this course. I will use this slide. And next, before we enter the general introduction to the concepts, let's go to the slide for some green policies and the course structure. Let me scroll down to the last page. All right. And let me share the screen again. Good. Okay, so this is the second time that I taught this course on Canvas. And I think Canvas is really useful it's really helpful to organize everything into modules. Okay, so for example, everything we will talk about today will be published to the module called Welcome and Introduction for today's, including today's lecture videos, the quiz questions, and any related pages if I think is useful. So that will be appear in the module called Welcome Introduction. Okay, and for the future content, say after in the next week, we're going to talk about Python and the Python environment setup, programming programming tips, programming tricks for Python and NumPy. So those will appear in another module. Okay, so that's the whole course will be organized into a sequence of related modules. So we basically will go through those modules sequentially, one after another. Okay, maybe one module in a week or one module covered by 2 weeks. Okay, so if you're not familiar with Canvas yet, you can on the Canvas page on the left side navigation bar, you will see the module button. If you click on the module, and you will see everything that's already published. So if you didn't see a module there, that means I didn't publish it at my end. But I will make sure that all the slides are uploaded to the corresponding module before each lecture starts. I see a question that, do we need any specific software IDE to develop? So yeah, good question. So we do use Python. Python is the programming language, and also it includes a bunch of programming, like a bunch of packages, useful third-party packages including NumPy and PyTorch. Okay, and for NumPy and PyTorch, those are the packages you need to install yourself, but we will have one slide covering that. So it'll be on next Tuesday. We will talk about how we set up our computational environments. And for IDE, for text editors, we don't have specific requirements, but for all the assignments, for all the programming assignments, we will talk about that later, because all the assignments will be in Jupyter Notebook, which requires you to install Jupyter Notebook, and it's basically a browser-based IDE, if you would like to call it IDE. It's also an IDE, and it allows you to do to execute Python code within cells. Okay, so that is a very neat and convenient way to do experiments in machine learning. Okay, so those are the softwares that we will need to use. Okay, so here it says that there will be quizzes in those modules, and those quizzes will be published usually after the published after the lectures are done, after the lecture videos are uploaded. So the quizzes will be a reminder, mostly for you to watch the lecture video. If you don't have time, or if you happen to miss the Zoom sections, okay? So I will make sure that I record all the lectures and upload it to YouTube, and I will post the YouTube to the Canvas page, okay? All right, so let's look at the grading policy, okay? So there will be 3 parts. First, assignments takes 75%, and there will be 9 assignments in total, okay? So all the assignments are program-based practices. So I will release each assignment with some code templates organized into a Jupyter Notebook, and those Jupyter Notebooks require you to launch and to fill in the code, to fill in all the missing code in order to execute the code correctly. And in the notebook, I also provide the expected I will also include the expected outputs for each task, so that you can immediately see whether your code is correct or needs fix after you have done your part. Okay, you just execute it and to see if you get the correct answer. So that is typically how the assignments goes. Okay, how the assignment look like. But the assignments still need to be submitted after you are done. If you get all the expected output, that's good, that's great. That means you do all the questions correctly, but you need to still upload the whole Jupyter Notebook before the deadline of the assignments. And our teachers, our TA will examine your notebook, and so that your assignments will be graded, okay? There's no automated grading system yet. It's really time-consuming to develop such a system. Okay, so all the notebook need to be executed locally on your computer, on your laptop computer. So that's why in the next Tuesday, the course on next Tuesday will be really important, because we are going to make sure that everybody can set up your programming environment correctly on your local computers. All right. Second part is final exam. Okay. So it's not a programming based final exam. Okay. It's knowledge based. It's a knowledge test based on multiple choice questions, okay? But that doesn't mean that you don't need to do computations. So there's some questions that require to do simple computations, but definitely you don't need to use write Python programs to solve those questions. You don't need to train a model. You don't need to like execute anything complex for the final exams. Okay, I see who raised your hand. If you have a question.
Yep. Just a quick question. Will we have examples of the final or anything similar to show us what kind of questions we should expect?
Mm-hmm. So yeah, I can probably provide some examples when we do the reviews. So the final covers the whole course. Okay, it covers all the chapters. So yeah, I can provide those example questions, but not in this stage because we haven't started yet. Maybe some parts near the final exams.
Yep, that's all I wanted to know. Thank you, Professor.
Yeah, no problem. All right. Okay. And the last part is quiz questions. It takes 5% of the total score. So those quiz questions will be, as I said, published after the video lectures are published. So it basically a checker, as a way to check that you have joined the Zoom session or you have watched the video lectures. Okay, so I think that's my last slide. Now I'm going to stop sharing and go back to where I stopped. Okay. Let me share it again. All right. So the goal, our purpose of the slides today is to have a general introduction to the concepts, okay, and to lay out the some necessary concepts and what do we say? What do we call it? A mind model for the so-called machine learning technology. Okay, so it's a technology that evolves really fast, really rapidly. Okay, so after the year like 2020s and before the year 2020s, 2010s, it's a huge difference. There's a huge gap between the performance of machine learning technology. So before the year, maybe 2009 or 2010, when people in academia or in industry talking about applying some machine learning models, we probably refer to support vector machine, SVM, or kernel methods, okay? But it's after the 2010s breakthroughs of deep learning or deep neural network, the game has been changed. So the deep learning technology appears and the convolutional neural network model and the recurrent neural network models, and later on the reinforcement learning, deep reinforcement learning, and so on. Those technologies, they all appeared, like, I wouldn't say they never appeared before, right? They could exist in mathematical papers or in computer science papers before, like maybe 20 or 30 years ago, but the real applications of those technology, of those deep neural network based technology really appeared after the years around 2010. Okay, so if you're interested about a brief history of deep learning, you can go to the posts that I show here and the timeline of machine learning. These are interesting visualizations for how the field evolves by showing the terms. Okay, so far it's okay because we don't have dived into the technology. We haven't dived into the the details yet, but only looking at the terms, it shows a very significant trend of evolving. Okay, so for example, if I search the keyword on Google and I use Google Trends to analyze how many people have been searching on Google, then if I look at the term artificial intelligence highlighted by the blue, right, and the machine learning highlighted by red, I will see that there is a very significant increase starting around the year of 2012. Okay, and before that, these two terms are not that frequently searched by Google, by people. Okay, so probably not to artificial intelligence, because the concept of AI appeared really early, around 1960s or 70s. People are doing research in AI, but there's a period called what's it called? It's a really an ice age period for AI, because at that time the computer hardwares don't support the highly amount of computation required by a successful AI model. So that's why AI has been hot in science, in academia, but then it's become less popular, and not until the recent breakthroughs around the year of 2012. All right, so there's some signature breakthroughs around that year. The NeurIPS conference in that year witnesses a lot of, especially the ImageNet breakthroughs, in which the computer vision tasks received a significant amount of improvements. Okay, so we will see that in the next page. Yeah, right, this page. So let's look at what happened during that year, 2012. So there's a release, there's a challenge called Large Scale Visual Recognition Challenge. Okay, it's basically to have scientists write computer programs to recognize the objects in images. Okay, it's a really simple from the perspective of human beings, but it's really been challenging if we want to write intelligent programs that recognize all the objects. Okay, so the related to this task, the LSVRC task, have been data sets released, which are the basis for testing the performances, right? After we write a program or write a machine learning model, we want to have a standard way to test the performance of it. And the ImageNet dataset is one of those kinds of testing datasets. And also it's being used to train the model as well, okay? But the dataset, the purpose of the dataset is to train the model and test the model so that a reliable score will be reported. Okay, so if we look at the typical performances of the proposed machine learning methods or machine learning models on the task of large-scale visual recognition challenge, you will see that the red line, which is the error rate, okay, error rate is the opposite to the correct rate, right? So we want to lower error rate. So the significant drop of error rate happens in 2012, okay? And along with the red curve is the blue curve that shows how many numbers of GPUs, so graphical processing unit, which is a chip on modern computers to support the image processing, fast speed image processing. So in that year, there are 4 GPU units used to train the really good model that makes the error rate drops from 26% to 16%. Okay, so that is a very significant improvement of performance in the large-scale visual recognition challenge. Okay, so that means a 10% accuracy increase. And after that year, the increase of performance didn't stop. Okay, we'll see that the error rate reaches almost less than 10%, almost to 7% in the year of 2014 to recognize objects in images. So it is a really successful breakthrough if you compare it to the year of 2010, 2011. So a 7% error rate is really an accurate performance. And the other side, we are using huge number of GPUs to support the training of such successful machine learning models. So here's a trend that I wish to show, so that the recent history of the evolving machine learning studies is kind of illustrated here. All right, so of course the course enrollments in academia is also a increasing trend. So for example, our course, we have more than 30 people still in the waiting list. So for that, I would like to mention that we will have, I don't know if in this room, if there are people from the waiting list joining us, but I do hope that we can have more people, as many as possible, to join the class. But we have limited TA supports, and so which means we have limited class size, and we will decide the final class size by the end of this week, okay, or early next week. Okay. And research papers, the number of papers, they are also increasingly in a crazy style. So if you compare the papers from all the other fields, if you look at the AI or computer science alone, they really increase in a sharp style. And it's actually no longer feasible to catch up with all the papers. Okay, because even in the top tier conferences of computer science, not every piece of paper is the paper that's worth your whole effort to reading it, to understanding it. And I would say only maybe 1% of it is those papers that worth careful reading, while all the others, there's some worth reading the abstracts, but most of the papers, they appear this year, and maybe in the next year they will be replaced by something new, something more, how to say, something brings more performance, or something that's brings more insights. Yeah, so that is how the current status of the field. Yeah. All right, so these two charts are the charts that I've shown are from maybe 2 years ago. If we look at newer charts or newer research recent years, like in last year or this year, I would say things could be a little different. Okay. All right. So why there's such a boost or such a dramatic increase, dramatic expansion or growth of the field? Why do we need such a technique called machine learning? So what does it mean for us, for everyday usage, for everyday life to people? Okay, so before we can have an answer to this big question, I would say why do we look at some examples that's the recent breakthroughs machine learning researchers have made. Okay, so this is the recent breakthrough from the company OpenAI.com, and it's called DALL-E, and it's a term combining the artist DALL-E's name and the Pixar's WALL-E. Okay, so it's a neural network that can create image from text inputs. So like I can type in a sentence like an illustration of a baby daikon radish in a tutu walking a dog. Okay, and these figures are generated. They are not handcrafted or not painted by human beings, but they are generated by the models that are able to understand the sentence. Okay, and also that is able to generate figures or shapes and colors that corresponds to the concept that's recognized in the sentence, in the input sentence, like a baby daikon, wearing a tutu, walking a dog. All those elements, they are first recognized, and then they are used as the inputs to generate the a series of figures.
That's incredible.
Yeah, so that is indeed incredible. I would say the backend technology requires huge amounts of training data and huge amount of training time. That's a lot of money, a lot of resources. And also, it doesn't mean that everybody needs to train that model by ourselves. And it's not practical that we can gain such a effect with the current hardwares we have. It's really impossible, actually nearly impossible to train such a model on your laptop, even on your desktop computer, because they require data, require GPUs to support the training. So, but the model per se, the model's architecture is not, I would say, is not super difficult to understand. Okay, I think after we have gone through this whole course, you should be able to have some rough idea about how these models, the backend models, look like. So you basically need a model to understand the natural language first, right? To extract all the keywords in the natural language in the input sentence, and then it should be able to generate. There should be a generative models to generate meaningful figures that are corresponding to the terms recognized. Okay, so hopefully by going through our course, we should be able to understand what the backend technique are utilized in this type of amazing amazing technology. Okay. Yeah, the second example is armchair in the shape of a avocado. Okay, so those are all fake images. These are not from real world pictures, but fake images generated by the models. So if you go visit their websites, there you will see more more interesting examples, which really provide really helpful, really powerful terms for art designers, say product designers. So if you need some new thoughts, you need new inspiration, by simply typing into some concepts, by typing some into some inputs into the model, and it will generate something that maybe are really inspiring to what you want to see, what you want to do, and it could be something that you never thought of before. Okay. All right. So that's the most recent breakthroughs from OpenAI. And I have 2 more slides. Also found on their websites. Okay. It doesn't mean that I'm a fan for their company, but it's really they did well in some technology. But Google, Facebook, what other companies we have? Microsoft, they all have amazing teams for AI research, for integrating AI models into daily usage, into daily products. Okay. So this example, let me see if I want to go through. Okay, so here we don't have a video. Yeah, in the next one we will have a video. So the second example is called Jukebox. It's a tool to generate music. So the mechanism is that it needs to, first of all, sample to sample from the real raw audio. Okay, so I think these audios, the inputs are the real audios, maybe played by an instrument, by a musician, using instruments, and those raw audios will be encoded by the convolutional neural network. Okay, and to obtain some compressed audio. So this will be the basis for generating some new music. Okay, and then another important part is the lyrics. Okay, so the lyrics will be something we compose. Okay, we manually compose. It is similar. So the lyrics used here is similar to the query used in the previous example, like a baby daikon wear tutu, walking a dog. So it could be some random words that I wish to use. So given these lyrics combined with the sampled music and with a well-trained transformer model and CNN decoder, we're able to generate some novel music piece, okay, which may carry out some semantic patterns, some patterns that make sense, some interesting patterns that the musician in this step never see. Okay, so it's a new way of thinking about creating arts, a new way of exploring the unknown field in the art. Okay, so in these websites, there are different soundtracks that you can use to click the creation from the AI model. Okay. All right. And let's see another example here. Okay, so I would like to play this one. So it's a recent breakthrough that's OpenAI trained from scratch to train a robot hand to play Rubik's. It doesn't use like explicit rules to define which way you should go, but it's purely from scratch. It's like if you using some mechanism in reinforcement learning. It's like if you get it wrong, then you have some negative scores, right, as a kind of a punishment. And if you did it correctly, then you get some positive rewards. Okay, so it's purely from scratch training results. Let's look at it.
We're trying to build robots.
Can you hear the sound?
We can, yeah. Thank you.
You can. Okay.
Yes.
Okay.
Yes.
Yeah, that's good. Okay.
That learn a little bit like humans do, by trial and error. What we've done is trained an algorithm to solve the Rubik's Cube one-handed with a robotic hand, which is actually pretty hard even for a human to do. We don't tell it how the hand needs to move the cube in order to get there. The particular friction that's on the fingers, how easy it is to turn the faces on the cube, what the gravity, what the weight of the cube is, all of these things, it needs to learn by itself. The interesting thing is that kind of standard techniques in robotics haven't been able to scale to that complexity that we see in a robotic hand. Humans have evolved to be able to manipulate and operate our hands. So there's a huge amount of learning that's happened through evolution to get us to this point as a species. And the robot has to learn all of this from scratch. Instead of trying to write very dedicated algorithms to operate such a hand, we took a different approach where we create thousands of different simulated environments and learn to do the task in all of those. And hopefully the robotic hand will be able to do it in the real world as well. This means like thousands of years of experience that this neural network has had in simulation. Every time the algorithm has gotten good at the task, we make the task harder. That's really crucial because it needs exposure to really complicated environments in order to eventually be robust to the real world. You put a rubber glove on the hand and can still carry out the task. This ability to generalize to new environments feels like a very core piece of intelligence. It really changes the way we think about training general purpose robots. Moving from thinking too much about the actual algorithms and start thinking about how do we create complex enough worlds where they can learn. At some point, then it would be more down to the imagination, what robots could actually accomplish. The hope is to build robots that can do many different tasks to increase the standard of living and give everybody a better life.
Wow. That's really amazing technique. Okay. So, and I don't think it's hard to accept or hard to anticipate, because similar techniques using reinforcement learning has already appeared years ago that support that use simulation to achieve some performance in simple tasks. Okay, and also this is because this is embodied into a mechanic hand, which means it's the models trained in the simulated environments can easily reflect into real world, and I would expect that these kind of robotic techniques would have huge impacts to our life. Yeah. So that's the recent breakthroughs that I wish to show you, to showcase what kind of machine learning based technique can achieve in the state of art of industry. Okay, so we are not going to cover, particularly for the Rubik Cube example, we're not going to cover the reinforcement learning technique here, because as I said, this is the current machine learning is a really huge field, and reinforcement learning here is, I would say, a specific branch that is more specifically useful in the field of robotics. Okay, in tasks that require some interaction between an agent and the environments, the reinforcement learning will be where it can where the model can be trained in the best way. Okay, but we will focus on supervised unsupervised learning that doesn't necessarily have the interaction parts, but the neural network based components in those supervised versus non-supervised learning tasks will be the building blocks, will be the building basis for more advanced techniques that the robotics rely on, robotics reinforcement learning rely on. Okay, so I see connections, but also as limited by our time, resource, we are not going to cover all the fancy parts in the field. Okay. Let me go to the next slide. So the self-driving car, I'm gonna go into play this YouTube again, but self-driving is really a growing field and it's getting more mature. So the videos that I embedded here was, let me see, it should be 3 years ago. I think it's from Waymo. Yeah, so it is a visualization of how the objects, how the other surrounding cars, surrounding pedestrians are detected by the models on the that are installed on the self-driving car, and how the paths, how the roads are perceived by the machine learning models. So I think this is a really fancy visualization of the technical details here. Okay, so we will anticipate. So it's easy to see that there are a lot of image recognition tasks going on, a lot of object detection going on, right? And a lot of reconstruction tasks. By looking at by recognizing the objects, how does the model reconstruct the 3D the 3D scenes that it can recreate in the computer's simulated environments. Tesla, not sure how Tesla's autopilot function. There's some sort of self-driving components in Tesla, I guess, but I'm not totally sure with its current progress. Okay. Yeah. So let's look at another case, AlphaGo, AlphaGo 0. So this is I would say this is a more astonishing achievements to me as compared to the robotic hands playing Rubik's. So because playing Rubik's is just a simple movement, it has a simple goal, but for complex tasks that require really long steps of computation, really long historical tracing tasks, and a very large scale of computation needed. Like this decision is not located into one position, one point, but it's a global optimal solution you need to find in a Go playing game. Then how the machine learning is used actually in this type of technique is really the fascinating part. So actually in AlphaGo and AlphaGo 0, the detailed machine learning model is actually not a super fancy one. It's just a deep neural networks that computes the policy, the rollout policy, and the SL policy, and the value network. So those are just deep neural networks, which is not fancier than any existing models. But by setting up the policy in a separate way with the value networks, we have two set of networks that computes the policy gradients in the middle. So those are the terms, but I wish to explain it a little bit. So these models, they are trained based on data that's the model played against itself. Okay, so it uses human experts as some inputs as the initial, it's kind of initial states, but based on these initial states, it plays like millions of games with itself, and use the results in those self-playing games. It can updates those weights in the policy network and the value network. So those networks become stronger and stronger. It's like workout in the gym. You always train your muscles, okay, by playing against yourself. But the strengths, the advantage of artificial neural network here is that it can train itself within a short time for thousands, for millions of games within itself or against itself. So it's really efficient training, and it's also no longer. That's why it's no longer astonishing that it can beat the top level human players within the Go game, like in a really easy style. Okay. So next videos. Those are the videos that found last year. So in those fake expression or fake face swap technique, it's been there for 2 to 3 years, I think, and there are generative components used in this technique. It's like generate something fake, but it resembles the authentic images really really closely. And these techniques are already used in the first example, DALL-E, right? In the DALL-E example, we need to generate something that's close to our concept. And here, the technology, the technique at the back end is something that's already appeared here first, okay, to generate fake images. I'm not sure if we can watch this. Okay, it's an external link, but so we will not watch it here. So if you're interested, you can following the links in the slides that I upload. Okay, so after so many examples shown here, let's get a little bit of theoretical arguments here. So it's actually not easy to determine to finalize the definition for what machine learning is, because our cognition for this concept is still evolving. Okay, so but I would say back to the 1960s, the conclusions pointed out by Arthur Samuel at that time is still a valid one, still applies to all the applications today. So essentially, we want the computers to gain the ability to learn, especially without too much supervision, especially without being explicitly programmed. That is, we don't set logic rules to tell what it is, to tell what to do, but it should be able to infer based on its previous experience. Okay, so a little bit more recently, I would say the scientist Tom Mitchell's quotes, I pretty much like it to be a description of what a machine learning program can do. Okay, so a computer that can able to learn from some experience with respect to some task, and these tasks can be measured by some metric P. Okay, so as long as we can identify these three elements, the experience and the task and the performance metric P, then we are kind of describing a machine learning scenario or a machine learning problem here. Okay, so if we use these keywords like experience, task, and performance, we can basically kind of define all the examples we have shown before. Okay, so I found these two quotes quite useful to summarize the machine learning techniques. That's all kinds of machine learning techniques that we are inventing and we are experiencing nowadays. Okay, so for example, in the facial recognition task, right, the experience for the program is all the face images of the same persons, right? And the task is to recognize whether an unseen image is the same identity, is the same person. And the performance can be measured by the accuracy, how much error, right? So the experience, task, and performance can be extracted as the 3 elements. So that means we can define face recognition as a machine learning task. Okay. So you can try that later on other different tasks. Okay. So from the perspective of students learning these concepts, I personally find that an easier visualized way can help understand machine learning in one figure or with one sentence. So I would say, if you are building something used machine learning, or you are building a machine learning model, then you are actually learning from the data. Okay, and it's not just a little piece of data; it's a lot of data. Okay, so what you have built is actually a model that contains a set of parameters. Okay, and those parameters indicated by the Greek letters theta 1, theta 2, theta 3, they are the components of the model. So they are the parameters that are used to learn from the data. Okay, and since we have such a huge amount of data sets, how do we feed the data into the model so that the model's parameters get trained, get tuned? Then it is the technical details we want to specify. For example, we can split the data into little pieces of smaller blocks, and each time we only take one block out and feed it to the model, and that model's parameter got changed, got updated, and then we take another piece, right, and into iteratively until the learning is done, or until the training is done, until we are satisfied with the parameters. Okay, so I would say these can be a model, a mind model that describes what machine learning does, at least to the content, to the scope of this course. I would say this mental model is quite useful to cover all machine learning tasks, especially supervised learning tasks. Okay, and the performance of the model can be measured on top of some new data. So this new data in this slide never appeared in the training data on the left. Okay, so I hope this slide you can watch the the charts and the connections and the whole figure on this slide, so that it helps you better understand what a machine learning workflow and what a machine learning model actually does. Okay, so let's go through the spam mail detection. I'm going to skip this part. This is part of my work previously, which used a machine learning based language model to estimate how much information there is in our utterance, in our language. Okay, which is also an application, which can also be described by the data versus task scheme. Okay, so let's skip this part. Let's skip this part. Okay, Word2Vec is something we're gonna introduce in the future. All right, so let's go to the recap. So when people talk about machine learning, and when we talk about machine learning in this course, we really emphasize the ability of a model that can predict the future and to predict the unknown from the past or from the known information. Okay, so the past is all the training data we have. It's the collection of examples, and the future, the unknown, is the information from some novel examples. So we do wish the machine learning models we trained can perform well on the unseen data. Okay, so in the examples we have listed above in previous slides, like to classify whether a male is a span or not, it's to predict the future, right? So in predicting whether words in a sentence, what the next word in a sentence is to predict in the future. To detect seismic events in the future. These are all applied machine learning techniques that use the future technique to predict use the past information to predict the future. Okay, so I do hope this figure on this slide is useful throughout the whole semester. Whenever you have an idea of a machine learning model, what a machine learning model is, this figure will help you figure out what actually you are doing. So we are trying to build something in the middle within a red box that uses these parameters to fit the data, to be tuned by the data. And the performance of these parameters will be evaluated by the new data, which is unseen during the training stage. All right, so yeah, we reached the end of today's lecture, and that's so much of it. So I will release the video later to Canvas, and then also the quiz questions will also be released. Yeah, question is, those new data are not just the conclusion of those unprocessed data, right? No, it's not a conclusion. It could be something very new. It could be something that never appeared. It could be some very novel patterns. So in those cases, the model may fail, okay, because the model has seen too much normal data sets. If there's some anomaly in the new data, then it is likely to fail. The syllabus quiz, I decided that, so usually I will set 2 days after the lecture is done. So it should be Saturday night. Yeah, so that's what I usually did for the quiz sessions, for the model quiz. Yeah. Yeah, that's usually, yeah, that's what I will do for every lecture. So that's for sure. That's to make sure that you keep track of, keep up with all the progress we're making. Yeah. Yeah, if you're on waitlist, I will basically cancel the due dates for the first module, for the quiz, syllabus quiz and the first quiz. Yeah. Any questions?
Is there a reason you went fast at the end, or do you not know that the class goes until 5:15?
Oh yeah. So I usually what the slides that are prepared are based on the topic that I used to teach in the face-to-face style, but I usually find myself talk faster in the online classroom. So I feel like it's inevitable. So
Okay, I'll
yeah.
interrupt you more in the next time.
Yeah. So if you want to fill up more times, that's totally fine.
Cool.
Yeah, I would be happy to answer questions. How that grades? Oh, I see some more questions. Are all of the programs single or all some pair? Not sure what this question means. Do you mean a single file or multiple files?
Like, do we need a partner? I think that's what he's saying.
Oh, no, all the assignments are single assignments. There's no team assignments or team projects. How are the grades classified? Range. So you mean the grading scheme? Like if you get 94 in total, then you get A? Is that what you are asking? So I think I will use the default. I will use the default grading scale of Canvas. So for AI, which I guess it should be 94.
Okay.
Points.
Yeah,
Yeah.
that's good. Thank you.
Yeah. So for the final, there will be no written problems. It's all multi-choice based.
Are we going to do any projects in the class?
No, there's no project. Yeah, that's because I actually tried 2 semesters for projects, but it didn't turn out really good. For projects, I wish. So I used to wish that we can form a team for 2 to 3 people, but sometimes the teams get too big, and sometimes people want to do single projects, and it's hard to control to have good quality control over the topics, over team members. Yeah, it's really not that practical for a class of 60 to 70 students. Yeah. So some of the assignments, I think they can be viewed as a minimal projects, something like that, because like a image classification task, you need to handle different parts. You need to handle the input part, you need to handle the training part and evaluation part. It's quite, I think it gives you a pretty minimal experience of what a machine learning project looks like. As the final exam, multiple choice, will we have a week or 2 do the lab assignments? Yeah, usually 2 weeks. 1 to 2 weeks. For each assignment. All right.
When will the first assignment be?
The first assignment will be released the next Thursday, after we are done with the Python environments, computation environments. Yeah.
Thank you.
Yeah, the first
So
one.
after class then?
After what?
After class.
Yeah, after class.
Got it. Yep.
Yeah. All right. If you think of any questions, send me an email. Yeah, I will upload the video to YouTube and then publish to Canvas. I know this is off topic, but what do you think about OCR with regard to machine learning? Yeah, I think the current state-of-art OCR uses some. So obviously, it should be convolutional neural network-based image recognition models. Actually, what we can try on our cell phone is Google's Translate. That if you turn on the video mode, it will let you take a picture and recognize all the characters, all the foreign language characters, and then try to translate it. So there's a very obvious OCR components embedded in that app. So those OCR components, I'm pretty sure they are neural network based models, because the neural network based models are, especially CNN based models, are the state of the art, the top performing model for recognizing image patterns. Yeah.
Professor, are office hours going to be by request only, or are you going to have some set hours that we can come to?
Yeah, that is to be determined. I will set up a 1 hour office hour. Yeah, it could be a Monday or Wednesday, sometime around 1 o'clock to 2 o'clock. Yeah, I will determine that later.
Okay, thank you.
No problem. Okay. Sounds good. So if you don't have other questions, I'm going to end the Zoom session and welcome. And it's glad to see people coming and hope you have a fresh start and good new year. And I do wish to go back to campus sometime soon. Yeah. And yeah, let's hope for the best.
Thank you, Professor. Have a wonderful day and stay safe out there.
Thank you.
All right.
Thank you.
Thank you, Professor.
Bye.
Yeah.
Thank you.